Thank you very much for the possibility that I can give this talk to you. My name is Lisa Lehmann and I'm a postdoc at Toulouse in the group of Jean-François. Today, I want to present you a new method we recently developed to diagnose the large-scale magnetic field for the Spiro legacy survey. So, are you seeing this bit here? So, to diagnose the large-scale field, we are currently using two main methods: the analysis of the longitudinal field and the Zeeman-Doppler imaging technique. The longitudinal field has the advantage that you can determine it directly from the line mask Stokes profiles, which is fast and easy. It provides you a first glance on the field strength, the complexity, and if the large-scale field evolves. But we have no information about the exact topology. That means, for example, the axis symmetry or how colloidal or toroidal the field is. These information can be provided by the Zeeman-Doppler imaging, by the ZDI technique, which is returning as a vector magnetic field mode of the large-scale surface field. But the ZDI method requires some experience for reliable results to be reached, and is based on a number of prior assumptions that may not be valid. For example, that the large-scale field is static across the time span of the observations. For the SLS, we were searching for a method kind of combining both, so it should be fast and easy to apply because we have many targets and long time series observed with Peru, and we wanted to have more information than on the with the longitudinal field itself. So we want to know something about the axis symmetry or the colloidal toroidal fraction, for example. And we find that the principal component analysis, the PCA method, can do this job. PCA is mostly known for his ability to reduce the noise, but we found if we apply this directly to the circularly polarized Stokes-V profiles, we can get some clues about the key information of the large-scale field. In the following, I will show you how this method works using simulated and observed Stokes-V profiles. So the first step is to compute the mean Stokes-V profile. If the large-scale field is axis symmetric, the Stokes-V signal is constant as the field is aligned with the rotation axis. So the mean profile catches this constant Stokes-V signal and is therefore sensitive to the axis symmetric component of the large-scale field. In the figures, you see simulated examples, Stokes-V time series in gray, and underneath in red, the mean profile, and in black over here, the mean subtracted Stokes-V profile. If you go from the left to the right, you see how the tilt angle of the dipole is decreasing from 0 to 90 degrees, using the same format of maps that Jean-François introduced in the beginning of the session. So you see, if the tilt angle becomes larger and larger, the mean profile gets smaller and smaller compared to the mean subtracted profile. So this gives you a rough estimate about the axis symmetry of the field, but the mean profile can even more. If you decompose it in its antisymmetric and symmetric part, which refers to the poloidal and toroidal part of the axis symmetric field, you get even this information. On the right, I'm showing one example mean profile, and if we decompose it now in the red poloidal, in the red antisymmetric shape, which is the poloidal field, which is dominating in this example, but we still see this blue component, so there is a toroidal field as well. If we increase now the amount of toroidal field, we see how the mean profile evolves from a poorly antisymmetric towards a more symmetric shape. If we go now from black to yellow, increasing the toroidal field. How does it look in reality if we use real observations? So here I'm showing the Stokes-V time series for CEBU. It's an early Endorf observed with Naval in 2008. And we see straight away the mean profile is quite strong compared to the mean subtracted profile. It means that CEBU has a very axis symmetric field. And if we decompose the mean profile, you see this profile is really antisymmetric, so poorly poloidal over here. The PCA analysis helps us now to analyze the non-axis symmetric part of the field and how it evolves with phase and time. So here you see the eigenvectors determined by the PCA and the corresponding coefficients. We see for this example, only the first eigenvector contains a signal, all the other ones just contain noise. And it is an antisymmetric shape over here. The coefficients show a sinusoidal trend, very typically for a dipole field. So with the two extrema, and this one here shows us that a negative pole is pointing at phase 0.8, 0.9 over here. If we compare this now with the ZDI map Donati et al. In 2008 determined, we see here we have really a polar dipole with a very tiny tilt pointing to phase 0.8, 0.9, as we expected to see from the PCA analysis. Comparing the coefficients with the longitudinal field, you see pretty much the same trend, which is usually the case for low recent eye objects as CEBU is. But you see the longitudinal field is a bit more noisier and the error bars are larger. I want to show you a second example. This one is again an early Android, nearly the same mass, but the same rotation period and recent eye, but showing a completely different field topology, observed with Naval in 2008 as well. So this is the time series of DS Leo. You see straight away the mean profile is smaller compared to the mean subtracted profile. So this meaning this field is not as axisymmetric as we see for CEBU. And you see straight away for the mean profile, this one is very symmetric. So this axisymmetric field is toroidal dominated. Checking out the PCA analysis, we see now that two eigenvectors contain a signal, the first two over here before we start to see noise. The more eigenvector contain a signal, the more non-axis symmetric the field. For DS Leo, the eigenprofiles show an antisymmetric and symmetric shape, allowing us to analyze different components of the large-scale field. And you see that the coefficients show here more than two extrema. So that means this field must be more complex than a dipole over here. Furthermore, the coefficients also unveil that we see kind of evolution in the field. So I color-coded the coefficients with rotation cycles, and we see that the coefficients for the orange and yellow cycles are smaller in amplitude than for the blue ones. So indicating that the large-scale field of DS Leo is decreasing in this time. We see the same trend again for the longitudinal field, as again, this is a low recent eye object. And our conclusions about a non-axis symmetric, more complex large-scale field with a strong toroidal component agrees with what we see from the ZDI map over here. Donati et al. Found that this star is evolving over a timescale of 1 year, but our PCA analysis unveils now that this star is even evolving faster on the timescale of its rotation period of around 14 days. In the second part of my talk, I want to give you a first look on the first results of the Spiro Legacy Survey with my method. I'm presenting here the late M-dwarf star JG1289, which has a recent eye of 2.4 and a rotation period that is very long, so 70 days we expect or something like that. And we would expect to see a weak, mostly static magnetic field as activity indicators like the X-ray flux or the large-scale magnetic field itself was found to decrease for long rotation periods. For example, by White et al. In 2011 or by Alini Vidotto et al. In 2014. But we see a completely different picture. For JG1289, Spiro was observing this target over the last 3 years, providing us an incredible data set of over 200 polymagnetic spectra. And I show on the left just a couple of these together with the mean profile. And now you already can tell me if the field is axisymmetric or not. So we have a significant non-axisymmetric field because the mean profile is quite small compared to the mean subtracted profile. And decomposing the mean profile now in its symmetric and antisymmetric part, we see straight away this field is polarizer dominated. We can even determine the maximum field strength of large scale toroidal field can have, it must be weaker than 15 Gauss, otherwise we would have seen it in the mean profile. The PCA analysis unveils now that we have two eigenvectors with a signal, meaning that, or confirming again, the field is non-axis symmetric or has a part of non-axis symmetric field that is good seen for us. And the first eigenvector shows a shape you're already familiar with, this antisymmetric shape, which is similar to the first derivative of the Stokes I profile. But the second eigenvector is showing a shape similar to the third derivative of the Stokes I profile. Both are antisymmetric, so we would assume that the field is really poloidal. And the coefficients over here, you see there's a lot of things going on. I color-coded them again with rotation cycle, and you see there is a lot of evolution from rotation cycle to rotation cycle. I want to focus on one rotation cycle in specific, the rotation cycle number 5. Here we see that in the first coefficient, it is not dipole-like. We have 4 extremes, so at least we have a quadrupole component. And also the second coefficient shows a nice trend over here, so the field must be very non-axis symmetric. I also want to show you, do you see this very steep slope over here and there? This is giving you a very good hint that this star is observed with quite a high inclination. Otherwise, we wouldn't be able to see such a steep change in the coefficients or in the longitude in the field. And for stars with a very low VCNI like JG1289, this is a valuable hint because the inclination is not well constrained for this low VCNI objects.
Lisa, you have 1 minute left.
Okay, this kind of topology is also easy, can mislead you to underestimate the rotation period. You can easily see that the rotation period can be just half of the rotation period it actually is. One rotation later, you see it's a completely different picture. Now we see it is more dipole-like. The signal in the second coefficient vanished, so that means the field must be more axis symmetric. And it extremely highlights how valuable this SLS survey is with this long observation campaign, because remember, this star is rotating with 70, 80 days. To cover more than one rotation cycle, you already need several months, more than 6 months, to see this trend. You can have some fun with Gaussian processes to get the rotation period. We found that for the coefficients, we get better results than for the longitude in the field. I proved our conclusions by determining the ZDI maps for rotation cycle 5 and 8. And indeed, we see a non-axis symmetric poloidal topology here with a tilted dipole and a strong and a significant azimuthal quadrupolar mode that vanished later on, but the dipole becomes more axis symmetric and stronger. This is what we conclude from the PCA method. The SLS discovered more of these very interesting objects, these androids with long rotation periods over 50 days, like Gliese 905, he also with rotation period over 100 days. But you see in the coefficient, there's a lot of things going on. So this will be a lot of things to discover here. Also, other androids showing evolutions on short and longer time scales, even cycles. So watch out what is coming. I leave you with my summary over there. The paper is under revision and hopefully will be on arXiv in the upcoming weeks. And thank you very much.
Thank you. One quick question for Lisa. So if not, we'll go to our next speaker. Thank you again, Lisa.
You're welcome. Thank you.